Yes, Chair. Okay, so let us welcome Shlomo Razamat from Technion. He's talking about generalized Schur partition functions and renormalization group flow. Please, Shlomo.
Thank you very much. So I would like to thank the organizers for organizing this meeting. I think last time I was in Trieste was on Zoom, and being in Trieste on Zoom and physically here is not exactly the same thing. So thank you for organizing the workshop and for giving me the opportunity to present this talk. So I will be talking about this paper with Anirudh Deb, who is a student of Leonardo Rastelli at Stony Brook. And this is some weird observation that we incidentally made. This will be the main point of the talk. So I will discuss various things that probably are trivial to most people in the audience, but then the conclusion is a little bit surprising, and we don't really understand the conclusion. Okay, so I will tell you some story with some results, and it's kind of experimental math results. So we arrive at certain observations that we cannot really explain. So if in this framework of an hour and 15 minutes, we will be able to explain them from your input, using your input will be great, but that is where I'm going to go. And again, I will tell you some trivial things, and the trivial things are due to me, and the interesting things and all interesting things are due to Anirudh. And I understand that Anirudh is applying this year, so have him in mind. Okay, so let me start from telling you various trivial things. Maybe as it is a first lecture in this meeting, this will be an introduction to all the rest of the talks in this workshop. Another thing I want to say, I will have, like the workshop is quivers, symmetries, and SCFTs. I will have to say something about symmetries and SCFTs, but no quivers. And sorry for that, and quivers is the next frontier. Sorry, Ami, that's something left for you. Okay, so what is the basic idea? What are we trying to do? So we are trying, as always in quantum field theory, we are trying to understand quantum field theories in their strongly coupled regime. So we want to start from some weakly coupled theory, and then we turn on some interactions, maybe renormalization group flow, maybe some exactly marginal parameters, and then the theory becomes strongly coupled, and we want to understand what happens beyond this wall of strong coupling. So we want to penetrate this wall and to say something about the physics behind this wall. So the idea is to devise some tools using which we can compute on the weakly coupled side of the wall something which will be invariant of this exactly, like some parameters which take us to strong coupling. For example, again, this can be couplings or renormalization group flow. So we compute something here, and it is still true here. So this is a trivial computation here, but tells us something about strongly coupled physics. And of course, we know many examples by now of such quantities. For example, without use of supersymmetry, we can try to understand how symmetries behave across these strong coupling walls, and more usefully, how anomalies behave across these walls. And of course, in recent years, there is a lot of progress generalizing these ideas of symmetries and anomalies, and much has been done. I will not be talking about this. I will rather revisit this older subject of looking at supersymmetric quantum field theories. And when we have supersymmetric quantum field theories, we have additional tools like this that we can devise. Usually they take form of some kind of a partition function. And usually these partition functions are related to some kind of counting problems. Also anomalies are related to some kind of counting problems. And it's actually an interesting open question, how much more these partition functions capture than just the anomalies. It's clear that they capture more, but how much more? I think it's not obvious, like maybe these counting problems are kind of generalized anomalies in a sense. And again, the idea is that all these quantities you can compute at weak coupling, and they're somehow independent of the values of the couplings. So there are, of course, we would want to compute quantities which depend on values of the couplings, but these are much harder to compute. So what can we deduce by computing these coupling independent quantities? So let me give you a couple of the examples. Again, this is the trivial part of the talk. So for example, these types of partition functions and these invariant tools in more generality are very useful to understand the notion of dualities. When we have two different descriptions of the theory, we can compute these partition functions exactly for two different theories. And if we assume that these two theories either describe the same physics on the same conformal manifold or they flow to the same theory, these computations have to exactly agree. So this is a trivial statement. Another kind of more interesting statement, which will be more relevant for this talk, this also allows us in some cases understand symmetries of the infrared fixed point. So sometimes from the computation here, we can deduce what will be the symmetry or what is likely to be the symmetry in the infrared. And this doesn't have to be the same symmetry as the symmetry in the UV. And in this way, we learn something non-trivial about the infrared fixed point. Okay, this will be important for this talk. So again, here is an example of infrared duality when we flow to the same theory, but there can be also conformal dualities. Again, please feel free to stop me at any point if anything is not clear. Even if I say that it is trivial, you should not be afraid to ask a question and to attack me in other ways. Okay, so now let me give you an example of a tool. Again, this is something which in this audience is very well known, but I will emphasize certain things that we take for granted. This will be important for what I'm going to say. So an example of a tool is what is called a supersymmetric index. A supersymmetric index is just a Witten index, which has exactly the properties that I advertised. You can compute it at weak coupling in the UV, and this is something which is invariant under continuous deformations such as renormalization group flow. So to compute the index, we just count states or operators in UV with certain weights, where the weights are related to symmetries that are preserved by the interactions or the renormalization group flow. And then the answer, the result of the computation, gives us some information about the infrared fixed point. So let me stress this property. So here is, for example, the arrow representing the renormalization group flow. And say we start with certain theory here. And it has certain global symmetry. And we turn on fugacities parameters for each one of, say, U1, the Cartan generators of the global symmetry for various U1s that we have. So we have many of these parameters, say A1, A2, and A3. And then we turn on some deformation, which, say, breaks one of the U1s, say the parameter for which is this A1. Then the only thing that we need to do in the index, we compute it in this theory, in the UV theory. And then we just set this parameter A1 to be equal to 1. Okay? So we compute it here. But then when the parameter A1 is equal to 1, the answer we computed here also is the supersymmetric index of the theory we will obtain in the infrared or on the conformal manifold with this particular interaction which breaks that U1. And of course, we can continue this procedure. We can turn on more interactions which break more symmetries. And all the indices that we would compute here, they come from this index of the UV fixed point, and we just specialize parameters. Okay? So importantly, the index that we compute here in the deep infrared also tells us about the UV fixed point. Usually, we don't think about this. We think about this arrow really going in this direction, that we want to deduce something about the infrared fixed point from the UV. This is the logical way how we do things. But it's important to know that this index that we compute here encodes some information about the UV fixed point. Okay, and the surprise that I will want to tell you about is actually will be going in this direction. Okay, usually we think that when we go from UV to infrared, we lose information, and we lose information. But importantly, we have some information which remains, which tells us about the original fixed point, and that information might be actually, like, there might be more information that we can naively guess. Okay, so that will be the surprise that I'm going to tell you about. Okay, any questions about this introduction?
Here you are showing that there are three
Why?
there are some three factors that you have to subtract such factors to get the right function.
So I don't, what do you mean by right partition function? Yeah, so I would say, like, if I start from some theory here, say it's an asymptotically free theory, nothing is free, and I flow in infrared, some vectors become free and some fields become free, I would keep them. Okay, so the CFT in the infrared might be built from some interacting piece and some free pieces. So for these arguments that I'm going to tell you about, I would keep everything. Okay, because if I strip this free part, so I kind of will lose some information about the UV fixed point. Okay, sorry. Okay, so let me go to the concrete setup that I will be discussing. So what I will going to tell you about is only true for four-dimensional n equal 2 supersymmetric quantum field theories. Okay, so let me introduce the supersymmetric index in 4 dimensions. So before that, the discussion was general, but now let us specialize to n equal 2. So this is the most general supersymmetric index that we can write for n equal 2 theories. Again, it's a very, very old story by now. So importantly, the n equal 2 theories have SU2R times U1R R symmetry, at least if the theory is conformal. And we have SU2 times SU2 isometry, space-time isometry, for which we can turn on various parameters. So the index has the parameters QP over T. So it's some choice of parameterization of fugacity, which couples to the U1R symmetry. There is this parameter T, which couples to the Cartan of SU2R symmetry. And this P and Q couple to combinations of these two Cartans of these two SU2 symmetries. So notice that we have only 3 parameters here, although we have more symmetries. And this is due to the fact that we want to compute an index, a type of Witten index. So the parameters we want to turn on should couple to charges which commute with some choice of supercharge, which I denote here by Q1. So all these combinations, they commute with some choice of supercharge, and they couple to a Q. So Q appears both here and here. So it will be J1 plus J2 minus R, has to commute with this Q1 and so on. So again, this index is usually defined for conformal n equal 2 field theories because we assume that the SU2R symmetry is there. Okay, but we can also think about it as in more generality as some kind of a special case of n equal 1 index with various symmetries that appear. So let me give you an example, again, a trivial example, which will be important for us of how this supersymmetric index is invariant under a normalization group flows. And the most trivial theory that we can consider is a free theory. So let's take n equal 2 theory, which is free, which is just a free hypermultiplet. So Q and Q tilde are half hypermultiplets. These are 2 chiral superfields, and the index, the superconformal index that we can compute for this theory takes this simple form. It is a product of 2 elliptic gamma functions. Elliptic gamma function is a special function which is doubly infinite product. Again, the details are not important, but it will be important that it is some kind of an infinite product, not a trivial rational function. And you can think of the numerator as coming from the scalars in the theory, and from the fermions in the theory and their derivatives, and the denominator from the scalars, or from the bosons rather, and their derivatives. So we take this theory and we want to turn on a mass term. We want to deform the theory with a mass term. We know that if we deform the theory in a mass term, in the infrared, the theory is gapped, is trivial. So how does it happen in the index? So in the index, the weight of the field Q and Q tilde is T to the half. If we turn on a superpotential, then the weight of the superpotentials is QP. This is something which can be derived. And then, in fact, to be consistent with this superpotential, we need to set QP equals to T, or QP over T to be equal to 1. If you look here, that means that we are breaking the U1R symmetry, basically. The fugacity coupling to QP over T, we are setting it to be equal to 1. So we do that in the index, and miraculously, the contributions of these two elliptic gamma functions cancel out. Okay, you can do this simple computation. You take these two gamma functions, the numerator of one cancels with denominator of the other. So it's a trivial consistency computation to perform. And then the index is just equal to 1. This 1 is interpreted as contribution of the vacuum. Okay, we only have the vacuum. We don't have excitations above the vacuum here. So everything is consistent, and this is a trivial example. Now, I mentioned potential deformations and superpotential deformations, where we take an index of a tirion, we set some fugacities to 1, but we can generalize it to Vev deformations. And the prescription here is slightly different. So if we have an index of a theory and we have an operator for which we want to turn on a vacuum expectation value, what we do in the index, we again set the weight of that operator equal to 1, but then the index will actually diverge. Okay, the idea is that the index, say if the weight of this operator is b, the way this operator will contribute to the index, but also the square of that operator, the cube of that operator, all the powers will contribute, and the index will have a pole which is 1 over 1 minus b. So what we do, we set b equal to 1, but that leads to a divergence, so we just look on the residue of the index. Okay, so this is a generalization of what we said before, and let us keep that in mind. Okay. So this was an index and the n equal to index and how it is consistent with the renormalization group flows. Now we'll look not on a most general index, but we'll look on a very particular case of the index, which is called the Schur index. And this Schur index is some kind of a magic wand. It's not, yes?
Can you give the example of that?
Yeah, you can give a Vev. So if you give a Vev to what do you want exactly to do? You want to give a Vev to a scalar, it will be a different, so for example, giving a Vev to a scalar, you will need to set t to the half times a equal to 1, for example. Okay, so it's a different thing to do. Okay, but then you take a residue, and then again you will get nothing, because you will get some Goldstone boson. So I'm a little bit careless. Sorry. So you can. It's not nothing. It's what you would call the Goldstone bosons. But in this prescription, you would need the prescription would be to take the residue and strip off the Goldstone bosons. So that's what you would need to do there. Okay. So it's important when you do actual computations of giving a Vev. So that it was like in a technical computation, you take a residue and multiply the index by some weird function, which will be like some hypermultiplet with weird charges, which would be exactly something like take a hypermultiplet and set this U1 fugacity to something. Any more questions? Okay. So let me consider this Schur index. Now, Schur index is a specialization of n equal to index, which is unrelated to renormalization group flow. So we said that if we want to understand how index behaves under renormalization group flow, we specify fugacities in some way. Here we specify these two fugacities T and Q to be equal, but it's unrelated to renormalization group flow. We can do it in any n equal to theory. This is unrelated to flows. This is just not looking on the most general index, not turning on most general parameters P, Q, and T, but just setting T equals to Q. Okay? What happens in this case is that the index simplifies in various ways. So setting T equals to Q, we lose one parameter, but actually when you look at the index, you lose another parameter. So although naively you did nothing to P, the dependence on P just can be shown to disappear from the index. P just disappears. And the reason is that this index in the Schur limit preserves more supersymmetry. And this parameter P can be viewed as in a similar way as this parameter beta appearing here. It will be just coupling to some anticommutator of two supercharges. And then by the usual Witten index logic, the dependence of this parameter P just disappears from the index. So this is one nice property of Schur index, which will be important. It is a more supersymmetric object than the usual index. Okay, on the other hand, from the definition of the Schur index, if you look, say, for example, here, when you set t equals to q and understand the dependence on p disappears, you can naively define that index without using U1R symmetry. Only SU2R symmetry and SU2J1 and SU2J2. So naively, this index can be defined for non-conformal theories also. So there was a paper, there is a paper, Michele is here, I didn't see Michele. So if Michele is not here, let me say some harsh words about Michele. So there is a very nice work of Thomas Dumitres called Guido Festucci and Michele Del Zotto from 2016, but there is no paper. So there is a talk on YouTube that you can find that Thomas gave at NatiFest, where they made this statement precise. So they made some localization computation and have shown how you can define Schur index for non-conformal theories. There is a talk, but there is no paper. If you are friends with Michele, please make Michele publish that paper, because it should be very interesting. Okay, so this is one thing. These are two things. First of all, the dependence on P disappears. It's more supersymmetric object. It can be defined for non-conformal theories. And then there are various other mysterious things. So naively, the Schur index is a very Higgs branchy object. For example, you can show that the operators which contribute to it, or some of the operators which contribute to it, are Higgs branch operators which satisfy this property. And you can also show that Coulomb branch operators do not contribute to it. For example, the weight of Coulomb branch operators which have this form, trace of phi to the power n, where phi is the chiral field in the vector multiplet. If you set q equals to t, then it will be contributing p to the n to the index. But we said that dependence on p disappears. So the contribution of this operator to the index has to cancel with something else in the index. Okay, so these operators, the Coulomb branch operators, naively do not contribute to the index. This is on one hand. On the other hand, there are several works by now, many works, which related the Schur index to some Coulomb branch computations. Most notably, this work of Cordova-Shao and some follow-up works, where the index of the Schur index of unequal two theories, which is something you count using the UV CFT, could be obtained by studying the Coulomb branch of the theories, say the BPS particles of the theories, and constructing something called KS wall crossing invariants. And there is a prescription to obtain the same quantity in these two different ways. One, which is very Higgs branchy, just counting operators, and these are the main guys which contribute in a sense, but then doing completely Coulomb branch computations. And there are other things that where this Schur index appears. For example, it is instrumental in this VOA CFT correspondence of Leonardo and friends. And more recently, it also mysteriously appeared in connection with SYK computation. There, I think, at least for me, it's complete mystery why it appears in that context. Okay, so this thing, it has a lot of nice properties, and today we will discuss one additional property. Any questions about this? Okay. So let me now discuss a certain puzzle that is related to this Schur index. It's a very simple puzzle. It's not, maybe it doesn't deserve to be called a puzzle, but let me call it a puzzle. So let us go back to this case of having a hypermultiplet and giving the hypermultiplet a mass. On one hand, let me start from the second point here. We already learned that if you take the full index of the hypermultiplet and set qp over t equals to 1, the index just becomes equal to 1. So the index trivializes. On the other hand, if you first set q over t to be equal to 1, and then set p equals to 1, the index is independent of p after you set q over t to be equal to 1. So in particular, it is consistent with setting p equals to 1. But doing these two things together is as setting qp over t equals to 1, and maybe something else. And in this case, the index is not trivial. Okay, it's some non-trivial function. It's some theta function. It doesn't trivialize. So doing these operations in two different ways, you don't get the same result. And moreover, the puzzle is, or semi-puzzle is, that the index doesn't trivialize. When for this theory, naively, the Schur index, again, is consistent with mass term, again, naively. But the specializing the index, like looking at the Schur index of a free hypermultiplet is not equal to 1. So the question is how this is possible. And of course, the answer is already in the statement of the problem. There is some order of limits issue here. So there are two limits that we can take. We can take this limit that I will call the mass limit, QP over T equals to 1, and the Schur limit. And in a sense, these two limits do not commute. Taking first the Schur limit, the index is independent of P. In particular, it's consistent with P equals to 1. However, first taking P equals to 1, the index is highly divergent. This is where this comment that I made, that the index is given by these elliptic gamma functions, is important. If you set P equals to 1 in this infinite product, the index will be just the same thing to the power infinity. So it's a very divergent object. So in a sense, setting first Q equals to T can be viewed as kind of regularizing this divergence. And then you get something finite. So there is an order of limits issue that we need to understand. Okay, so there is no really a puzzle here, but there is a feature of the Schur index. Again, it goes back to the fact that P, like the Schur index doesn't depend really on P. Okay, is this clear? Okay. So since we have this regularization with of this divergency by first setting Q equals to T, one can wonder whether there is another way in which we can take this limit, which is consistent with the mass deformation, which is not the Schur limit, but something more general. So we want to take a limit where P goes to 1 and Q goes to T, okay? And we will do it in the following way. We will take P equals to 1 minus epsilon, and in the end, we will send epsilon to be 0. And we take T equals QP to this monstrosity with some parameter which I take to be alpha here. And you can consider the index of the hypermultiplet in this limit, and in this particular limit, the limit is finite. When alpha is equal to 0, this is just a mass limit. Okay, you can see it explicitly here. You first set T equals QP, and then you send P equals to 1. So first you set the mass, like you take the index to be consistent with the mass, and then you set P goes to 1, so everything is finite. Something which is a little bit more complicated to see, but it's easy to do this computation. If you send alpha equals to 1, you get the Schur limit. Of course, you can see it from the result, but you can also see it from this expression, which is here. So this alpha is some parameter which can be taken anything you want, and it interpolates between the mass limit and the Schur limit. So it's a more general sort of regularization of these two limits. Maybe regularization is the wrong word to use here. Like you have some singularity, and alpha parameterizes some set of ways to get to this singularity in such a way that the final answer is finite. Okay. So for any n equal to index, you can consider this result. And in fact, this type of limit was already considered by Cecotti, Song, Waffa, and Yan 10 years ago, when they tried to understand this connection between the Coulomb branch computation of the Schur index using this Kontsevich-Soibelman invariant. When they try to understand that story a little bit in more detail, they also consider this limit. I can talk about this a little bit more. Maybe let's do it in the plus 15 minutes later on. Okay, so when we do this, when we take this limit, we don't do anything for this parameter Q. So the index will have still expansion in this Q, in general in half integer powers, but the coefficients of this expansion will be some functions of this parameter alpha. And in particular, they don't have to be integer for general values of alpha. They will have some values which depend on this parameter alpha. Now, this was for a hypermultiplet. For the gauge theory, this limit is more tricky, and the reason is that this limit of QP over T going to 1 is also consistent with giving vacuum expectation values to trace phi to the n, that is going on the Coulomb range. Okay? Again, this is because, as I already mentioned, QP over T is the weight of this field phi in this n equal to index, so setting this to 1 is consistent with turning on a VEV. That means that for a gauge theory, the limit that we are considering actually will lead to some divergence. So for a gauge theory, the way we will define this limit, this generalized limit that we'll call generalized Schur partition function, is taking the limit and stripping off the divergence which comes from going on the Coulomb range, from the fact that we have a VEV for this operator. So this will lead to some pole-like divergence, so we just strip off the divergence, and that is the result that we will get for general quantum n equal to quantum field theory. So it will be an integral over the Cartan generators of the gauge group, and the integrand will be something to the power alpha. This something, when we take alpha equals to 1, is exactly how you would compute the Schur index. And then in this general case, we take this thing to the power alpha. Importantly, also the Haar measure is taken to the power alpha. Everything is taken to the power alpha. This is not something we cook up. This is something which comes up out of this computation. We just compute this limit of the index, and that's what comes out. Okay? And then we can study this particular limit. It makes sense for alpha equals 1, it's sure. For alpha equals 0, it must. But then this particular expression makes sense for any value of alpha, for any real value of alpha. You need to be careful, of course, with, say, rational and irrational values of alpha. For example, the way to compute this partition function, the only way I would know how to compute it is doing this integral numerically. Like the pole computation doesn't work anymore for general values of alpha. Yes? So by alpha equals, so giving a mass, I mean just give everything a mass. So go on the Coulomb range first, like all the fields become massive. So the only thing you have is U1, like it's U1 to the power of the rank of the gauge group. So that's what will remain. This is the integral which remains. And then there will be some factor with Goldstone mode and so on that you need to strip off. But this contribution that you have here is just like without the integrand. This integral is literally rank of the gauge group, number of U1 vector fields. That's all that remains. So that is the mass, like mass for the matter. Okay, either directly giving a mass or going to the Coulomb branch and getting the mass explicitly. So we cannot distinguish between mass, giving literally a mass term, like adding a term mq tilde to the Lagrangian, to the superpotential, and turning on these waves. Oh, did something wrong. Okay, so I cannot distinguish between these two operations. If you wish, in the index, both of them are done by setting QP over T equals to 1, and we cannot distinguish what did we do. It's like there are two different procedures that we can do that are manifested in the index in the same way. Okay? So it's like being able to, like, we know these type of things when we have two superpotentials which break the same symmetries. So we can, like, just computing the index, we cannot distinguish what we exactly did, like what are the relative coefficients of different parameters that we had. Okay, so this is the limit that we want to consider. So again, this part of the talk is rather straightforward, and now we will try to understand what can we actually get by studying this quantity, this generalized Schur index. Okay, and here we will go into the realm of experimental mathematics or experimental mathematical physics. So we defined these partition functions, and we want to understand what does it encode, and for that we will do an experiment. What is an experiment? We will take some simple quantum field theory, let's say n equal to SCFT, SU2, SQCD. So one of the simplest interacting conformal field theories with a Lagrangian, which is explicitly n equal to supersymmetric that we can consider. which is not a free theory, and compute this partition function for it. And the question is, in the spirit of what I started with here, like that if we compute a partition function, it tells us something about all the CFTs that we have along the renormalization group flow. So the question is, can we capture something about the different CFTs on the renormalization group flow trajectory, which here includes the whole of the Coulomb branch of the theory, by computing this limit of the index with the parameter alpha? Okay, and here we will get a certain surprise. So first of all, if we compute this partition function with this, the second argument of the partition function is this parameter alpha that I mentioned. If we set it to 1, we compute the Schur index. So if we compute the Schur index of this theory, we get this result. I want to stress one thing about this result. If you look at the coefficient of Q in this expansion of the index, it gives you the dimension of the global symmetry group of the theory. Okay? This is something that you can rigorously prove, modulo some assumptions, just from representation, superconformal representation theory. Okay, that the dimension here, that the number here comes actually from the moment map operators of the n=2 theories, and the number of this operator is given by the dimension of the global symmetry group. So now this is the index of the theory, the Schur index, alpha equals to 1, but now let us play with different values of alpha. And the computation that we did, we said, okay, for general values of alpha, we will have an expansion in Q with numbers which will be general numbers, like general irrational numbers, for which values of alpha, the coefficient that we will encounter here will be integer. Like, again, you cannot scan all the possibilities, but you can scan some natural combinations of rational numbers. And you find, yes. So, for example, for alpha equals 1/5, this computation is numerical. Like you compute, you do the Q expansion that you can do analytically, but then the integrals are computed numerically. Okay? So it's a little bit slow. I mean, people who are good with numerical integration probably can do it faster. So the numbers you get here are actually 1.00 whatever. And then you do increase your numerics and you convince yourself that it is equal to 1. But you know, this is numerical computation. Okay, for integer alpha, this can be done as usual, but for numbers like 1/5, also for 1/2, I believe it can be done analytically, because the problem is the Haar measure. So you take the Haar measure to the power alpha. So the Haar measure for SU2 is like sine squared. So with a half, it will be just sine or absolute value of sine. So you can do it nicely, but with 1/5 and 1/3, it's the only way I know how to do it is numerically. Okay? So you do this computation numerically. You find that for 1/5, you get integer coefficients here. You do 1/3, you get integer coefficients. 1/2, you get integer coefficient. You do 1/17 or 5/17, the coefficients are not going to be integer. Just experimental result. I cannot prove it, but it's not integer. So, okay, you get integer results. And then you ask the following question. Okay, this is something which might be a Schur index of some theory, because the coefficients are integer. Okay, is it a Schur index of some theory? And it so happens that every time we get integer coefficients, it's related to some interesting physical theory or physical object. So in these cases, when you take alpha equals 1/5, it's the index of what is called the A0 Argyres-Douglas theory. When alpha is equal 1/3, it's A1. When alpha is equal to 1/2, it's the A2 Argyres-Douglas theory. Okay, these are Argyres-Douglas theories, which you can obtain by going on the Coulomb branch of the SU2 SQCD. Okay, these are theories which are down the RG flow from the SU2 SQCD theory. Now you can ask, okay, why to take fractional values of alpha, which are smaller than 1? Let's take values of alpha which are bigger than 1. And here also there is a surprise. If you take alpha equals 2, 3, and 5, you obtain these nice things. So now remember, if we are to interpret this thing as a Schur index of some physical theory, the coefficient of Q is the dimension of the global symmetry. So here you get 78. 78 is the adjoint of E6. So, and in fact, this Schur index that you compute here is exactly the Schur index of Minahan-Nemeshansky E6 theory. So Minahan has the fest this week. So let's honor Minahan by mentioning his name. Okay, so you get exactly that theory. You put alpha equals 3, you get the E7 Minahan-Nemeshansky theory. If you put alpha equals 5, you get the E8 Minahan-Nemeshansky theories. In fact, you can flow by exploring the Coulomb branch of these theories, you can flow to this SU2 SQCD. These theories are up the renormalization group flow from the SOA theory, this SU2 and F equals 4 theory, which has global symmetry SO8. So you can flow to this theory starting from these simpler theories. Yes?
Well, sure. About these theories is that these expressions are components of the vector value modular form.
Yes, this, let me get make a comment about this soon in 2 slides. But, yes. Hi, Palash.
Your observation, but you're missing F2 and G4.
No, I don't. I will have it on the next slide. So.
Can you find things which are
They are not related Barragh flows. Experiment.
so that play the games.
Yes.
You try variables that do all possible values you could try, and then find something new.
We didn't find something new. Well, there is one case that we found, but it's not here. Maybe I will mention it here. Maybe I will not mention because I don't remember the details, but it's in the paper. I will mention something about this. Well, exhaustive is hard because you need to go over all the, the guess would be that rational values of alpha are relevant. It will be hard to imagine that for irrational values of alpha something nice will happen. But then, there are too many possibilities. You can try to devise some kind of program of going over things systematically. But, okay, but if I don't mention it, ask me again about something. Okay, so now to the question I was asked. So the theories that I mentioned here, the values of alpha I mentioned here correspond to physical theories that we know exist. But actually, here is a more complete table. These are the values of alpha for which we get integer coefficients. And all of them, like these cases correspond to VOAs, but not all of them correspond to physical theories. For example, E8, like we get a Schur index of the certain VOA with E8 global symmetry, which happens to be related to the E8 Minahan-Nemeshansky theory. Then there is something called E7.5 VOA. We don't know of a physical theory for which it gives the Schur index. But actually, we get for alpha equals 4, we get exactly the vacuum the character of the vacuum module of that VOA. We get E7, E6, and then we get a 4 and G2. Again, these are not physical theories. These exist as VOAs, but I don't know of a physical theory for which these things for which these things arise through this VOA n equal to SCFT correspondence. Then we get at A2, A1, and A0, and there is something weird called A half. And very recently, Cho, Maruyoshi, Nardoni, and Song found an n equal 1 Lagrangian, an n equal 1 theory, which reproduces all the known information about this kind of theory. The same A and C central charges, something which looks like a Coulomb branch operator with the right dimension and so on. And the Schur index of that theory is consistent with n equal 2 supersymmetry. But this theory is not appearing there in the classification of Coulomb branch geometries that was done. So it might be that this theory is just an n equal 1 theory, which looks like n equal 2 theory, but it's not really n equal 2. So I don't know what is what will be the final status of this theory. Okay, but one gets all these results, and then there is this more general statement, which take any theory which sits on this sequence. It's called the Deligne-Cvitanovi sequence. Compute this generalized Schur index as a function of Q and alpha, and any other theory is encoded in this generalized Schur index just with another value of alpha. Okay? So again, you have this sequence of theories which are related by renormalization group flow, and any index is encoded in any other index, but with a different value of alpha. There is some non-trivial map of these alpha parameters. Again, this is an experimental observation. I don't have a proof why it has to be so, and soon I will tell you that it's not always so. But this is an observation for these particular theories. Okay, any questions about this statement?
Is there some way you can capture this using anomaly because you're really mapping the 4 decentral charges?
Yes, so very soon I will get to anomalies. So when it works and when it doesn't work, it's related to anomalies, but again, it will be an experimental observation. Oh, sorry, I went too far. Okay, so one thing which is weird here, let me even go back farther. So this theory has an SO8 symmetry, but it seems that it knows that it comes from a theory with E6 symmetry, E7 symmetry, and E8 symmetry. There is no statement that this theory has E6, E7, and E8 symmetry hiding. Okay, it clearly doesn't have these symmetries. But somehow, if you massage the partition function of this theory, you can see an E6, E7, and E8 in this partition function. Okay, and very particular, when you set the parameters to be very particular, for example, alpha equals 2, somehow you see representations of E6 appearing. If you set alpha equals 3, you see representations of E7 appearing, and so on. So somehow it knows about it. So you can actually try to understand it. So for the SO8 theory, for this SU2 SQCD, you can very well understand where the 28 comes from. Again, these are just moment maps. You can count the moment maps, and you can see this 28. So then you can go to this E6 theory and ask yourself where the 78 comes from. So in fact, this I that I wrote here has a hat. This hat means that we normalize the index by the constant term. So if you just compute the generalized Schur index, it will not start with 1 because the integrals are not done with Schur measure. So we normalize by this constant term in the index. So you can compute where this 78 comes from. And it is a very weird computation that we don't understand. Some of it comes from moment maps that appear certain number of times. Some of this comes from gauginos. There is some very weird contribution which appears here that when you normalize by the constant term gives you 78. And similarly for E7 and E8, it's some very weird computation. If you actually go and try to see where the numbers come from, for me, it's not very insightful. Like, it's not, the symmetry is not there. There are no E6, E7, E8 moment maps, but these numbers somehow appear in the end of the computation. Okay? So this is something that one can try to understand. Yes? Yes, so let me tell you exactly what we are doing. So we're computing this, the index of the SU2 SQCD as a function of Q with some value of alpha. But then we normalize, like, we could have done it in principle with E6 or E7 or E8. And then the claim is that if you compute for SU2 SQCD with alpha equals 1/5, it would be the same as computing for Argyros-Douglas theory with alpha equals to 1. And the map is actually more general. You can take here a general alpha, but then these two alphas that you would put here would be related by this factor of 1/5. Okay? And in some cases, we can check it. For example, for some of the Argyros-Douglas theories, there is the Maruyoshi-Song Lagrangian that using which we can compute the most general index, and then we can actually check that it works for any value of alpha. Okay, so let me make various, again, experimental observations. When we take alpha, we compute this index for a particular theory and take alpha bigger than 1, one obtains theories which are up in the RG flow from the theory, like E6, E7, and the E8 Minahane-Meshansky theory relative to SU2 SQCD. If you take alpha smaller than 1, you obtain theories which are down RG flow from that theory. In some cases, we get known results, like for these Argyros-Douglas theories that I mentioned, that for which we can compute anything because we have Maruyoshi-Song Lagrangian. But for E8 theory, Minhan-Nemeshansky theory, we don't have a Lagrangian which would compute the full index. We know the Schur limit, the MacDonald limit, different limits of the index. And if you wish, this type of statement gives a prediction for certain two-parameter specialization of the index. One parameter is Q and another is alpha. So this limit of the index. Okay, so it would be interesting to check this relation. Now, I think to Palash's question, it so happens that when you compute this index, this generalized index as a function of alpha, it solves the same, it solves certain LMD, so certain modular differential equation, with alpha as being a parameter for that equation. In general, the Schur indices and indices with inclusion of certain surface defects, they solve this modular differential equation. In fact, this gives a vector valued modular form. So the different entrants of that vector valued modular form correspond to the index or index in presence of surface defects. And here, if you wish, this generalized partition function solves that equation for any value of alpha. Okay, it's not clear why it does that, but that's what it does. And then, like, tuning this parameter alpha, you can go from SOA to E6 to E7 and to E8 and to Argyres-Douglas theory. Yes?
So the sort of quasi-modular form expression that we wrote down, does
Yes.
this alpha can be...
I don't know. It's a good question. Like how, so Palash, like if you, since these indices have some modular properties, you can expand them in some basis of modular functions and using, for example, Eisenstein series. And for known theories, one can do that. And the question is, with alpha, can you expand this index in terms of Eisenstein series? I don't know. It's a good question. Okay, this is one question. This is one comment that I want to make. Then the question is like that. I gave you the index. I did one experiment, starting with SU2 and F equals 4 SQCD, and things seem to work in some bizarre, nice way. Is it a general statement? And the answer is no. There are other rank 1 theories that one can consider. For example, SU2 n equals 4 theory. It's also a very nice rank 1 interacting theory that we can study. You can compute the index, this generalized index as a function of alpha, and for no value of alpha, you get integer expansion of the index except alpha equals 1, okay? However, then n equals 4 super Yang-Mills sits at the bottom, or almost at the bottom of certain Coulomb branch sequence of flows. There are theories more complicated n equal to theories that such that if you explore their Coulomb branches, you can get that theory. So there are theories up the renormalization group flow from this SU2 super Yang-Mills, but these types of games just don't work for this theory, okay? So it's not a general statement that it always works. So now you can ask, when does it work, okay? So this is an experimental result again. We looked on a variety of theories, and again, ask when two theories which sit on the same Coulomb branch, these generalized Schur partition functions are related in this way. And the experimental observation is that if their anomalies are related in a simple way, so both A and C anomalies here, I only write the C anomaly, so they are related by this relation, and their dimensions of their Coulomb branch operators are related in such a way, then the generalized Schur partition functions of the two theories are related in a way that we stated before, like in something similar to this statement. So for rank 1 theories, for this Deligne-Cvitanovi series of theories, these conditions work and theories are related. For SU2 super Yang-Mills, these conditions are not satisfied, okay? Now, you can ask whether only for this rank 1 Deligne-Cvitanovi series these conditions are satisfied, and the answer is no. So, for example, there are various generalizations that you can consider. For example, instead of SU2 with 4 flavors, you can consider SUN with 2n flavors. And then there are certain Argyres-Douglas theories which are related to this, and certain strongly coupled SCFTs. This SCFT is a generalization of E6 Minhan-Nemeshansky theory. And the generalized Schur indices of these guys are related by this parameter alpha. Instead of looking at SU2, you can look on USP2N, and there is certain generalization. And again, there are various theories that are related. So I think here, to Ami's question, we found something, I think, with alpha equals 2, which is, has integer coefficients, and we have a guess what is the theory to which it corresponds to. And there it would be a new result, but I don't. I think in that case it's rank 2, but it's in the paper. I don't remember the details, so I don't want to say. Okay. So in principle, like going up the RG flow, if you take alpha equals integer, the computations are easy, so it's easy to explore. But if you want to explore fractional numbers, if you don't go to higher rank, you need to do higher rank numerical computations, and oh, good luck. We didn't have a lot of luck, but the errors accumulate very fast. So I don't know how to do that in a systematic way. Okay, so the statement is that this surprise happens quite a lot, but doesn't always happen. Okay, there are some conditions when it happens and when it doesn't happen. And again, the question is why? So I'm in the realm of 2 minutes, right, Sergio? Oh, 2 plus 15. Oh, no, pardon, yes. Okay. So let me go to the 2 plus 15. Okay. Okay, so let's make more comments. So one comment is, once we understand that we can access this partition, like Schur indices, for example, of interacting SCFTs by considering Schur indices of other SCFTs by playing with these parameters alpha, we can kind of play these games iteratively. For example, we have learned that setting alpha equals to half for this SO8 or SU2 SQCD with an F equals 4, we can obtain some Argyres-Douglas theorem. That is something I said before. Then there are claims in the literature, if you take 2 copies of this theory and you add some free matter and you gauge a SU2 subgroup of the global symmetry group, you obtain Argyres-Douglas theory of a different type. So then by playing these games, you can obtain the generalized Schur partition function of this theory. So you take the free matter that you add with the parameter alpha, but then this extra thing that you add is the Argyres-Douglas theory with parameter alpha, but it is the SU2 SQCD with parameter which is alpha over 2. So you can play various games like that and produce novel results. Yes, I mentioned this. Okay. So this is one thing you can do, and we played it a little bit, but there are many more things that, that one can do. Another thing that I want to mention is that what we did, we just took the the full index of some n equal to theory, and just took certain limit of that index. We didn't do anything funny. In particular, for example, if we are in this class S story, these indices have to satisfy various identities due to S dualities. For example, this SU2 SQCD that we have discussed corresponds to compactification on a 4-punctured sphere of A1 2,0 theory. And that has certain dualities where you exchange punctures in a particular way. In the index computation, that means that you can exchange certain parameters for SU2 symmetries in the index. The integrands are not clearly invariant under that exchange. They are not invariant, but the integrals have to be invariant. This is something which had been proven by Van de Boelt long time ago for these SU2 theories, and more recently by Reins and Rosengren for SUN generalization for this statement. And you can check that this is true also in the limit. Again, this is something that had to happen in the limit if we did the computation correct. But it is some mystery. Again, this type of an identity which was known for Schur index actually works for any value of alpha. So again, I stress that the integrands are not invariant under this exchange. But if you take the integrand to any power alpha and perform the integral, the integrals are invariant. So I find it a little bit amusing. I don't know why it works. Again, it follows from known mathematical result because we just take a limit, but it is some weird statement that one can make. So let me summarize, and then I will answer the questions in the remaining time. So we have discussed the generalized Schur partition function. Again, this partition function was defined by Chakotay, Yan, Waffa, and Jae-Won Song a long time ago in a different context. But here we revisited computation from a different perspective, trying to understand this behavior of the index under mass deformation. And this partition function is just defined by taking this limit of mass or Schur limit or combined limit of the full index of a theory with certain regularization parameter alpha. And it seems that in various cases, this index that we are computing is consistent with certain deformation, with certain renormalization group flows. It's an experimental result. It's an experimental non-trivial statement that one can make. However, we don't know why and when exactly it works. There are some experimental rules that we came up with. We don't know whether they are correct or not. Again, for a lot of examples, it works. So the question is why and when it works. And this is something that we are working on, but we don't have good ideas. And for example, some things which don't appear in the paper, I told you that for alpha equal positive, everything seems to be well defined, but for alpha negative, it's not clear. So alpha negative means that we take this here some negative power, and then we will have poles on the contour of integration. So numerically, I would not know how to deal with this, but Anirudh did a lot of work. For example, one can do certain computations, compute expressions as a function of alpha for positive alpha, and then do analytical continuation to negative alphas. And there are nice results that one can obtain also for negative values of alphas. So there are many things that one can do, but we are still in the business of doing experiments. We don't really understand what is really going on. So thank you. And I hope the Italian is correct. It's ChatGPT.
Are there any other questions? Okay, Federico.
It's not very nice talk. So when we have a BPS prefab, we can compute by on the Schur index, especially for the channel we find in states. And you compare the different BPS.
Yes, so this is related to Chakotay et al. Work from 10 years ago. And there are people like Hee-Yeon Kim and Jae-Won Song, they are working in that direction. So the story in that, the relation that Chakotay and friends suggested is that there is this monodromy matrix, which is related to this computation of Kontsevich-Soibelman. And the trace of that monodromy matrix gives the Schur index. And then the question is, what if we compute trace of that monodromy matrix to some power? What does it give? And the claim was that these people, Chakotay et al., they computed that thing, and they took this limit with alpha being negative integer and introducing Wilson lines. So they did some computation, which is a combination of what I presented with negative integer alpha and introducing Wilson lines. They introduced the Wilson lines not to have poles, basically, because the poles come from the Haar measure to negative power. So they basically introduce something which will cancel those poles. And they found, again, experimentally, some relations to these monodromy matrices. And again, with Anirudh, again, it's mainly work done by Anirudh. Not mainly, it's work done by Anirudh, and I play with my ears, and I don't know, I listen to Anirudh. So one can try to connect, with general values of alpha using our types of computations without introducing the Wilson lines. And again, you find experimentally that there are relations, but we don't have a a complete picture in that case. For example, if you put in Wilson lines in this class S picture, there is no invariance under duality anymore. Because say if you put a Wilson line here, it will translate to a 't Hooft line in a different duality frame, and this identity will not hold. But in the games that we are playing, everything is invariant under S duality, for example. So there are subtle differences from what was done 10 years ago and what we are doing now, But yes, there are many relations also to this Kontsevich-Soibelman picture, but we don't understand the story fundamentally.
The example that you showed that didn't work, the input theory,
Yes.
mean that it gets correct. So
Okay.
is it always the case?
This is a good question. So we went through this thing, like what is special about the cases which don't work? They have extended Coulomb branches. They do have this, have that. So maybe, I don't know. Maybe that is a reason, I don't know. Okay, but it doesn't, these cases that didn't, all the cases we know don't work, they don't satisfy this anomaly and dimension of Coulomb branch operators that I mentioned. It might be a red herring. There might be some more fundamental reason, or actually that this is the right answer and this is only works in some cases and not. So I don't know. We played a little bit, but really, really little bit. Again, the reason is that once you go to higher rank, it's much harder to perform computations for non-integer values of alpha. So, but we played a little bit. So one thing we try to do immediately, so we have this Deligne-Cvitanovi series. It's called actually Deligne-Cvitanovi, rank 1 Deligne-Cvitanovi series. So we can try to go to higher rank. So that would be like instead of SU2 with 4 flavors, is USP2N with 4 flavors and anti-symmetric. So there things are more complicated and they don't seem to work in the way that we did do them. However, with the help of Hitchell, I think we will make them work. It's a generalization. What would you consider the simplest? We have 15 minutes.
The notion of applying the smile. This is the applying type of find the smile, and there is a find type.
Mm.
So you have to be the similar to generalization, which hopefully will have some.
And it will, like, the generalization is going to higher rank, or like?
Higher rank, but the combined find.
Yeah, so for high rank, like there is a classification done by Martone, Argyris, and friends, and so these theories, if you put n equal 2 here, they are rank 2 theories. So they are part of this. There is a finite zoo of say rank 2 theories. So these Deligne-Cvitanovi rank 2 theories are not theories which appear here. So, but. These are not these are some other theories, but okay, can discuss.
It would take me some time to precisely say.
In this series, if you set n equal on the left or n equal 1 on the right, you only get 4 examples, but you are previously.
Yes, so not every example, like E78, don't generalize in this case. So E6 is generalized to this R2 to n minus 1, but E78, we don't know how to generalize. Yes. That's true. So this, I think, all the Argyris-Douglas cases are generalized here, if I'm not mistaken. But going up, not everything we found a generalization. Maybe we missed something. Maybe it's just not in these sequences, but in some other sequence.
In terms of the theories that you know, the T-type conformal matter would be a good fund. So the one that have
So a quiver theory. So we tried quiver, like SU2 times SU2 conformal theory. Like SU2 with 4 flavor, like a linear quiver with 4 and 4 and bifundamental.
some of just to take D5 conformal instead of D4, get 48, take D5 conformal.
But I think this, am I right? SU2 linear quiver with 4, it's D5, no? I mean, a quiver theory, which is like this. Something like this was, you need to put the right. Yes. like make it conformal, and this we tried doing.
Classes would be.
I think it's maximum, minimum the compactification for dimension of type conformal method. So it's maximum, and minimum functure.
Okay,
But
but what is it's a Lagrangian theory? Or?
So
okay.
Dimensions would be, low dimensions would be.
Okay.
First question is, maybe you can reformulate that. So you started from SU2 flavor, and you can go up or down, but you could have started from 40E8.
Yes.
Then just go down.
Yes, in principle, but we don't know the full index. So to define the computation, you need the index which depends on P, Q, and T. Yes. And from it, you should be able to derive everything. Yes. But we know it only for E6, we know it actually. So we know it for SO8, for this SU2 SQCD. And we know some nice Lagrangians due to Maruyoshi and Song for Argyres-Douglas theories. Starting from any of these Lagrangians, we can get anything. There are also several Lagrangians, say, for example, for E6 theory. One is due to Gabi, another due to Iñaki and friends. And there it was complicated for us to take the limit. The limit was very singular, so it was we could not take the limit in a nice way. In principle, it should be possible to do like this. The Lagrangians are very weird for E6 theory. So it just, since the limit is very singular, like taking in a proper way is not a trivial thing. For Maruyoshi-Song Lagrangians, it so happened that the integrand, once you take the limit, the integrand collapses to be something very simple. But for these other Lagrangians for E6, and in fact there is also Lagrangian for E7, I think also due to J1 and I don't remember. It's technical difficulties there, but you know, sometimes technical difficulties turn into conceptual difficulties. So I'm not sure until that is done. But for E8, we don't know a Lagrangian depending on like an n equal 1 Lagrangian. Yes. So we have no way to compute the index depending on all the parameters.
Other questions? Sorry, one more question. Can we interpret this alpha like a number of analog of number of flavors? Like usually, if we imagine that we go down,
yeah, some effective number of flavors.
But because what we did is actually like some of a mass goes to infinity, and so each mass goes to infinity and goes down, then easier to understand what's going on.
Yeah, this is a good comment. I don't know if, yeah, effectively, yeah, you can think of it maybe as effective number of flavors. I don't know if this is computationally useful way to think about it. One maybe comment is that, you know, what we did, we took some of the parameters to 1. Okay, we kept Q and we took some parameters to 1. Taking all parameters to 1 is a 3D limit. Like that's how you would go. You take the index and you will go to 3 dimensions. So this limit is some kind of intermediate limit between being in 4D and being in 3D. And this alpha can be thought of some real mass parameter for certain combination of our symmetries. Okay, so this is one kind of really physical way to interpret the alpha. And then this limit of the index, you maybe can think of it as some kind of a Q deformation of the S3 partition function that you can compute, some very particular Q deformation. So I don't know so we took it as a limit of a 4D theory, but then you can think, can I start from 3D S3 partition function and somehow define something which depends on this alpha parameter, such that alpha is the real mass and Q is some deformation. I don't know.
Not before thanking Shlomo, lunch is upstairs. Okay.